In this video, I will show you how to find the resultant vector when two vectors are acting together, even when the directions are not simply north, south, east, or west. I will be using this four-step process and this nice graphic organizer to keep our work organized. A boat is moving at a speed of 55 miles per hour at a direction of north 50 degrees east. It encounters a 20 mile per hour wind at a direction of south 70 degrees east. Find the resultant speed and direction of the boat. Well, here comes my graphic organizer. Boom! And the way we set it up is we have a column for each vector. So we have the velocity of the boat, so I'll just call this column boat. And then we have the velocity of the wind, so I'll make a column for the wind. And then of course we're supposed to find the resultant speed and direction, so I'll just call the final column resultant. Now in the first row, we will record the magnitude and the direction. And whenever we do this chart, this direction has to be the type of direction that's measured counterclockwise from the positive x-axis. In the last row, we will convert everything to component form, horizontal and vertical, like this. Okay, now this chart goes perfectly with my four-step process. So step one is to determine the magnitude and direction for each vector. All right, for the boat, we have a speed of 55 miles per hour and a direction of north 50 degrees east. So magnitude and direction. So I will go ahead and record that 55 miles per hour for the magnitude, but for the direction, I will not simply write down north 50 degrees east, because as I mentioned, we need the type of direction that is measured as an angle from the positive x-axis. So we need to do some conversion. North 50 degrees east. Okay, so down here I will work it out. So north 50 degrees east means start at north and then move 50 degrees towards the east. So if I start at north and I move 50 degrees towards the east, okay, so this is going to be 50 degrees, then my vector is going to be in this position. Now, the angle that I will record on my chart, which I will refer to as theta, has to be the angle that is measured from the positive x-axis. So if this is 50, then this angle must be 40 degrees, and that's the angle that goes on the chart. Okay, so the direction is 40 degrees. So let's do the same thing for the wind. Okay, so 20 mile per hour wind, so we can go ahead and write that down. 20 mile per hour wind, that's the magnitude. The direction is south 70 degrees east. So let's work on that. South 70 degrees east. That means start at south and then move, turn 70 degrees towards the east. So the position of the vector would be here. So if I want the direction to be written in a form that's measured counterclockwise from the positive x-axis, what do I need to do? So this is the angle that we call theta. And here, so far I've gone 180 degrees, 270 degrees. All right, so I'm going to start with that. And then to get to my vector, I would have to go an additional 70 degrees. That's 340 degrees. That's the angle that we put on the chart for the direction. So we've done step 1. Step 2 is to convert the magnitude and direction to component form using the formula r cosine theta, r sine theta. All right, r is the magnitude, theta is the direction. So for the boat, if I want to convert this into component form, r cosine theta, so 55 cosine 40. And then r sine theta, so 55 sine 40. We can evaluate this on a calculator. So here I've typed it into my calculator. So there's my horizontal component and my vertical component. And I record that on the chart like this. Let's do the same thing for the wind. So again, r cosine theta, in this case, will be 20 cosine 340. And then r sine theta, so 20 sine 340. So again, we will use a calculator. So here we have the horizontal and vertical components, which we record on the chart like this. So we have now completed step 2. So step 3, we add the vectors to find the resultant vector in component form. So we're simply going to add these vectors together, which is easy to do in component form, and we will record that answer right here. So of course I am just adding the corresponding components. I'm adding the horizontal component with the horizontal component, and I'm adding the vertical component with the vertical component. So that turned out to be 60.92 and 28.51. So that's it for step 3. Step 4 is to convert this component form to magnitude and direction. So I need to just find the magnitude and the direction of this resultant vector. So I will calculate the magnitude over here. And I can simply use the magnitude formula. So 60.92 squared plus 28.51 squared. You know what? I'll just put that in the calculator. That's 67.26. So that is the magnitude, 67.26. And we are talking about speed, so this is miles per hour. Now we need to calculate the direction. Okay, so for the direction, I'm going to make a little diagram down here. Notice that I have a positive 60.92 and a positive 28.51. That means I am going to the right and up, or east and north. So that's going to put me in the first quadrant. So I'm going to go ahead and draw my vector into the first quadrant. So now let's go back and make a little triangle out of it. And this is the angle that I want. Sometimes I have to subtract from 180 or add to 180, something like that. But this is the angle that is measured from the positive x-axis, so this will be fine. Now, the horizontal component is 60.92, so that will go here. The vertical component is 28.51, so that will go here. If I want to find this angle, I can use tangent. So the tangent of that angle should equal 28.51 over 60.92. So therefore, the angle itself should equal the inverse tangent of 28.51 over 60.92. Calculator. So that's 25.08 degrees. So that is the direction theta, 25.08 degrees. However, this will not be my final answer because the way they gave us direction was they used the format north, 50 degrees, east, that type of thing. They weren't giving us the direction as an angle measured from the positive x-axis, the way we had to use on the chart. So before we write our final answer, we need to take this direction and write it in this format. So let's look back at the diagram and see what we can come up with. Now I would like to use the angle that we already have calculated, this 25.08 degrees, that's right here. So we could think of this as starting at east and then turning towards the north. So we could write this as east, and then we turn 25.08 degrees towards the north. So this is how we could write this same direction using the format they gave us in the original problem, which we must do. So east, 25.08 degrees north. So I'm just going to rewrite this whole thing. So, so my final answer, magnitude and direction, will be 67.26 miles per hour at east 25.08 degrees north. Kabam! There's the final answer. All right, let us move on to problem number 4. Lucy walks on a bearing of 090 degrees for 100 meters, and then on a bearing of 180 degrees for 180 meters. What is Lucy's bearing and distance from her starting point? So let us use our graphic organizer to keep our work straight. So we have the trip can be divided into 2 separate trips, and we'll have a vector for each part. Step 1, we determine the magnitude and direction for each vector. For the first trip, she walks 100 meters, so that is the magnitude, 100 meters. Now the direction, she walks at a bearing of 90 degrees. But we need to convert that to an angle measured from the positive x-axis. So let's do that down here. She walks at a bearing of 90 degrees. So a bearing of 90 degrees would be like this. So actually, that's due east. A bearing of 90 degrees is the same thing as directly to the east. So an angle measured from the positive x-axis, this would actually be 0 degrees. So we'll just put 0 degrees. Now normally when I write my component form, I do r cosine theta and then r sine theta. But that is not necessary when you have a vector that is either north, south, east, or west, because the entire vector is only one component. It only has one component, horizontal. So since there is only a horizontal component, that means the entire magnitude is the horizontal component. So I'm just going to put 100, comma 0 because there is no vertical component. Okay, let's move on to trip 2. So then she went 180 meters at a bearing of 180 degrees. Okay, so 180 meters at a bearing of 180 degrees, and now I'm realizing that that again is going to be a quadrantal angle. A bearing of 180 degrees is like this. Okay, that is a bearing of 180 degrees. So that means due south. So this is only a vertical component. So first of all, if I think of this as an angle measure that is measured from the positive x-axis, this would be 270 degrees. Okay, so I could write that down. Okay, so this is 270 degrees. However, for the component form, because I only have a vertical component, then I'm just going to put 0 for the horizontal component. Okay, and so I'm going to put the entire magnitude as a vertical component. Because this is going south or down, this is going to be negative 180. Don't get confused with the degrees. It just was a coincidence that she walked 180 meters. Okay, so 180 meters due south. That is a negative 180. Okay, so fine. We have now turned each vector into component form. And so that is the second step. The third step is to add the vectors. Okay, that's going to be easy because 100 plus 0 is 100, and 0 plus negative 180 is negative 180. So that is going to give me the resultant vector of 100, comma, negative 180. So the fourth and final step is just to find the magnitude and direction here of the resultant. So let's do that. Magnitude. For the magnitude, we can just use the magnitude formula, which is 100 squared plus negative 180 squared. Calculator. I'm getting 205.91. So that is the magnitude of the resultant, 205.91 meters. So that's how far the total walk was. Now let's talk about the direction. This represents 100 meters to the east and 180 meters south because it's negative. So we are talking about a vector in the fourth quadrant. So go ahead and draw yourself a vector in the fourth quadrant. And then let's talk about the horizontal and vertical components. So the horizontal component goes here and the vertical component goes here. So we can easily calculate the reference angle, which I will call R. Okay, so right now we are finding the direction. Okay, so we know that the tangent of R is going to equal negative 180 over 100. Now I'm going to ignore the negative sign because I just want the positive value of R. So the measure of angle R will equal the inverse tangent of 180 over 100. Calculator. So I'm getting 60.95 degrees. Now that's just this reference angle. So normally what I would do now is I would calculate the direction from the positive x-axis. All right, this is called theta. And I would calculate that by doing 360 minus the reference angle of 60.95. That gives me a direction of 299.05 degrees. However, that is not the type of direction that they gave us in the original problem. They gave us bearing. So instead of writing a direction as 299.05 degrees, we need to figure out what this would be as a bearing. So remember that bearing is measured from the north in a clockwise direction. So let's switch it up and figure out what would the angle be if we measured it in this direction. Well, right here at east, we were at 90. All right, so the bearing should be 90 plus the reference angles. So 90 plus the 60.95. That's 150.95 degrees. Okay, so that is what we need to use for our final answer. Okay, so I'm just going to rewrite the whole thing. So magnitude and direction, so we have 205.91 meters, that's the magnitude. Now the direction, you have to go ahead and use the word bearing whenever you're doing bearing. All right, bearing of, I forgot what it was it 150? 150.95 degrees. Okay, and that is the final answer. So you can just go ahead and put a box around that. Hey guys, that's going to do it for this video. Go ahead and click over here to watch the next video, and click over here to subscribe. That way you'll get every new video delivered right to your home screen.